Well, welcome everybody. I'd love to introduce Hanli Liu from NCAR, National Center for Atmospheric Research, who's going to be discussing, the way they simulate the atmospheric processes of the entire, the entire Earth. Welcome, Hanli.
Thanks, Greg. Thanks for the invitation. And today this is the title. I'm going to talk about our recent work on small-scale gravity waves and how it connects the atmosphere and our space environment. And I want to first thank my co-authors on this work or works. A few works I present here: Peter Lorenzen, Francis Vitt. They're both from NCAR, and Joe Huba from Scientech Technologies. Okay, so here's the outline, and I will first try to give you some background on both the role of the waves in the atmosphere and then our model, WACCM-X, whole atmosphere community climate model with thermosphere ionosphere extension. And then I'll try to motivate the study by pointing out some outstanding issues in representing waves and the wave effects. And the results will be here. We'll try to show how we can gain some insights from the high-resolution simulations, especially on the perturbative effects of the waves and also their effects on the large scale, the general circulation, the transport, and the composition. At the end, I'll maybe give an outlook on how to do better than what we do now. So if you have been to or haven't been to NCAR, this is the NCAR building, the Mesa Lab, and if you walk in the building, one of the, I think the south wall, there's a mural and showing the whole atmosphere environment. So you can see the different atmosphere layers from the troposphere all the way to the thermosphere, and also the ionosphere, the ionized part of the thermosphere called the ionosphere. And just from this figure, it seems everything's pretty empty up there, but actually it's far from that. We know that the LEO, the low Earth orbit satellite, that's where it moves around, and it actually, even though the atmosphere seems to be very thin, but it still exerts a lot of drag force on those satellites, and also space debris, which could be a hazard for satellites. And so you want to know the density very accurately to help specify the space environment or even predict that. And then the other, this is a schematic showing the other important aspect of the space environment, mainly the ionosphere. It concerns the telecommunication and also navigation and positioning. If you have anomalies or irregularities in the ionosphere, that could impact all this, the modern technology. Sorry. And another important aspect is the downward coupling, downward transport. And in a magnetic storm like the one over the weekend, a large amount of NOx or nitric oxide could be generated from the precipitating particles, and that can be transported downward in principle by dynamics in the polar night region, and NOx or nitric oxide can destroy ozone in a catalytic way. So that can be very important for the middle atmosphere or even lower atmosphere dynamics and chemistry. So those are some of the important aspects in understanding, try to better specify or characterize the whole atmosphere space environment. And so one thing we do is try to develop models to describe such a system. And these are some of the challenges. And of course, if it's a whole atmosphere model, at first you need to be able to describe the climate and the weather system. So first of all, it has to be a global climate or weather model. And then in addition, we have a third dimension. It really extends vertically quite a bit. So the depth of the whole atmosphere from the surface to the axial base, where things start to escape, hydrogen start to escape, is about 700 kilometers. So that's about 1/10 of the Earth radius. And if you look at the density and pressure difference from the surface to the top, it's about 13 order magnitude difference. And one way, maybe it's easier way to think about that, is to think of the scale difference between the penny and the proton. That's the spatial scale difference is about 13 order magnitude. And apart from that, there are also very different characteristics between the physics processes and also the driving. For example, at the surface, we're mostly experiencing visible light, IR, the heating, but up there, it will be X-rays and solar UV. So very different driving there. And also, I'll not go into details, but we have complex couplings between dynamics and chemistry, like the ozone driving in the stratosphere, and also ion-neutral coupling, especially in the ionosphere region. Another very distinct feature higher up is that usually the temporal and the spatial scale can be much shorter or smaller, and things are faster. So for a whole atmosphere model, you need to take all that into account and be able to account for all those different processes. So the model we're working with is the NCAR Community Earth System Model, CESM. And of course, atmosphere is a big component, but also ocean, land, sea ice, land ice, all those different components, and it's coupled together through a coupler. And for the atmosphere, there are three components we usually use. For the climate studies, more traditional, conventional climate studies, people use CAM, the climate atmosphere model, or sorry, that's a community atmosphere model. And that extends to the lower stratosphere. And then built upon that, there's a WACCM, whole atmosphere community climate model that goes to the lower thermosphere. And the WACCM-X goes to the upper thermosphere, to the exobase. And the science goal for WACCM, developing WACCM, is really to study the solar impacts on the Earth system and understand the coupling processes between different atmosphere layers, and to understand the implications of this coupling to both to the climate system and also to the space environment system. And this is, ignore all the details, but just to show you the kind of the model framework, the structure. So we solved the fluid equations, the Navier-Stokes equations, using the dicore. And then there's interactive chemistry in the model, and also neutral physics modules, and then ionosphere physics modules. And then we can run at different resolutions. I'll maybe talk a bit more about that later. And then once we build the model, seems we're happy because things seems to be on this Earth. It's not deviate really badly. So the basic structure looks okay. But there are a few issues. I want to point out a few issues here. So this one is a comparison. First of all, it's looking at a very important quantity that's important for the space environment called O2N2 ratio. It's a ratio between atomic oxygen and molecular nitrogen. It really represents the kind of the abundance, relative abundance of molecular species and atomic species in our space environment. And this is a comparison between a GUVI, a satellite measurement, satellite called GUVI, measure UV and in the thermosphere, and the earlier model called TIEGCM. And that's not a whole atmosphere model, that's an upper atmosphere model. But you can see that even in that model, we already see the overestimation of model results of O2N2 compared to observations. And that problem persists. We kind of inherit that problem in the new model, in the whole atmosphere model, WACCM-X. This is a more recent comparison between GOLD, and that's another satellite that's still flying, and WACCM-X. So you can see that GOLD is quite much lower in its O2 ratio than WACCM-X. And that's a problem because the composition determines the density. So that means that our model, the current state is that we cannot really describe the density very well. And another problem is the nitric oxide. I mentioned earlier that this could be important for the middle lower atmosphere dynamics. And this is a comparison of a WACCM. It's not even WACCM-X yet. This is a WACCM with a pretty well specified upper boundary condition of nitric oxide. But compare that with yet another satellite results, SOFI, which measures nitric oxide in the middle atmosphere. This is altitude. And we see that even though the general structure looks reasonable, but if we look at the quantitative results, this is at the south polar region. So this is the polar winter. So if you look at the polar winter, there's a severe underestimation by WACCM, by the model. And another issue is that the irregularities. So what's shown here are measurements of the ionosphere by two different satellites, GUVI and GOLD. And in both, and this is what the so-called equatorial ionization anomaly. There are two peaks on both sides of the magnetic equator. So that peak we know, we have, I think since the 1930s, it was discovered around that time. And it's also called the ionosphere fountain effects. And what's interesting or important for space weather is this mesoscale structures, the streaks in the ionosphere, and you see that also very clearly in the GOLD measurement. And that concerns the thing I mentioned earlier, the anomalies that's important for communication, navigation, etc. But all these features cannot be represented by our current model, just because of maybe because of both the lack of resolution and of lack of physics. So yeah, there are issues. There's a problem or problems in the model. So so that's that. And to maybe better look at this problem is to take another perspective, another view of the whole atmosphere from a wave perspective, a wavy view. And this is a schematic from McCormick et al. Recent paper. And they showed very nicely how the waves, various waves, are generated from the lower atmosphere. So for example, these are the gravity waves generated from deep convection. And these are usually mesoscale waves. And I should say, the gravity waves are buoyancy waves. It's a 2D version of that is what you see on the ocean surface. You see those buoyancy waves. And the 3D version, the internal version, internal wave version, is the gravity wave that propagate from its source and carry momentum and energy to far field, to the space. And one thing that does when it propagates upward is that as the atmosphere density decrease exponentially, their amplitude would increase just to conserve energy and energy flux. And that's kind of very similar to what you see by the seashore when you have less ocean or water mass. When the wave hit the shore, it will become bigger and crash. So it's a similar idea, and you have a surf zone usually in the mesosphere, and where the wave break and they make it generate secondary waves that can propagate further up. So apart from those small scale waves, there are also planetary waves and tides. Those are better captured because the size is much bigger, so they are resolvable directly by the models. So anyway, so from this perspective, we know that there are waves there, and we have some basic understanding of the wave. They're using linear theory, and we know that they're important because they carry momentum and energy fluxes from the source region to somewhere further away. But what's challenging is that the gravity waves themselves have a pretty big span in scale size, like from tens of kilometers to thousands of kilometers. At the same time, you have an environment where you have very large scale waves, tides, and planetary wave. And both kind of waves, they have impact on the global circulation and also on the whole atmosphere system. So the challenge is to try to quantify such a process with a very large spatial scale difference. And for example, for the gravity waves, they are highly dynamic. They're tied to weather systems. They are global. They're almost everywhere. And but their occurrence may depend a lot on what's going on.
So,
yes.
Can you give an intuition for what causes, like, what's special about gravity waves and what causes them, and also planetary waves?
Yes. So the gravity waves, almost anything in the atmosphere that has vertical movement can induce gravity waves. Of course, they depends on the scale of the source. The horizontal scale of the source, the horizontal of the gravity wave can be different. Like if you here, if it's a wind blowing over the mountain, then the gravity wave has certain characteristic scale related to the mountain. Or if it's from a deep convective system, then that's the scale of the wave. So that's basically how it's generated. Another way of generating that is a frontal system. Again, that frontal system have a lot of vertical movement, and that can kick off gravity waves. And even aurora heating, if you have a intense heating in the here, that can generate gravity waves. This schematic doesn't show that, but that can generate waves. And
intuition, I'm actually thinking is turbulent flow. I should be thinking anything that just causes these vortices to come up vertically through any kind of bubbling thing. But
yes, bubbling. Yeah, that's right.
Here.
Yeah.
Got it.
Planetary wave, on the other hand, idealized way to generate planetary wave is a flow around the mountain. So planetary wave, that has a different restoring force. So I mentioned earlier, gravity waves, they have the buoyancies, their restoring force. Planetary wave is a Coriolis force, so it's more like a horizontal movement. And tides is a large scale. So tides actually has a lot of characteristics very similar to gravity waves. But they are, here we talk about thermal tides, the solar heating, the day-night difference. That heating difference can generate a global kind of gravity wave. You can think of that. And but also the tides, the ocean tides, can have some impact. Usually it's not as strong as the thermal tides from solar heating, but they do play a role sometimes. You can see them in some special cases very clearly in the upper atmosphere.
Wait, so the ocean tides push up the air all the way up to the upper atmosphere?
Yes, they push up. The ocean tides will, yes, they have oscillation themselves, and because the air is in direct contact with them, so the air also have an oscillation. It's very small, lower down, but as I mentioned earlier, that's a first principle of studying whole atmosphere is that anything going up, it will get amplified because of the decreasing density, decreasing air density. So when you get up there, the tide, the gravitational tide or the ocean tide can become more significant.
I see. Wait, so when you say this is counterintuitive, that you have lower density means it's amplified, but do you mean in force or in extent?
Oh, the magnitude. So you maybe intuitive way to think about is that you think the total energy density, which is density times, say if it's kinetic energy, would be density, air density times u squared v squared, the wind squared. So if that quantity more or less is conserved, and then when you have when you roll, when your density is decreasing exponentially, to compensate for that decrease, the wind perturbation have to become bigger. So that's why actually I have animation later. When you get up there, the wind is really, really strong, much stronger than we experience here, mainly because of the.
So for momentum to be conserved, when there's fewer particles, those particles have to move much faster.
That's right, because That's right. Yeah, that's a good point. I think if you think of that way, let me think. So yeah, so I think it's just because you have less mass but same amount of energy, and then your particles need to jiggle faster. Actually, you do see that. Actually, I was thinking of the seashore, the surf zone, right? When the ocean get thinner, or I mean shallower,
Yeah.
you get to the shore, you have less mass, but the wave energy is about the same. So that's why you get the much bigger wave amplitude when you get to the shore and then break at the end.
Yeah, tip of a whip, you can get the break the sound barrier at the tip because it's so tiny.
Right. Yeah,
Okay.
I think maybe I'll think about that. That's a good analogy, right? Yeah.
Cool.
Yeah. Okay. So that's that. So that's a wavy view, and which is very important. You don't see that. That's also a difficult part of the wave view. You don't really usually you don't see the waves. You see composition, but it's harder to observe waves directly if you don't have a surface to see that. But also on the multi-scale aspect, this is our kind of a new model we're developing called SEMA, System for Integrated Modeling of Atmosphere. And this schematic was intended to show that we're trying, with the new model, we were trying to use the same model framework, but to capture a very vast span of scales. And for space environment or whole atmosphere modeling, it's actually here. We are trying to of course, go to very broad scale, but a lot of times our time scale is very short. Hours to days, maybe weeks. But this is something we really want to capture in this scheme. And currently, this is what we can do using our usual model setup. And so you can see we're missing most of the gravity waves. And that has, of course, impact on the circulation, transport, composition, and air density, etc. And we do have some parameterization to try to represent some of the effects, but it's really poor. It's really caused a lot of bias because of the oversimplification of the problem. And also, I should say that the gravity wave is not just important for the upper, thermosphere, ionosphere. Even in the stratosphere, maybe you heard of this oscillation in the equatorial region called a quasi-biennial oscillation in the stratosphere and the upper troposphere. So QBO, and that cannot be really well captured by this model setup. You really have to tune your parameterization very, very hard, try to get a signal of that. And then the other problem is that the polar region, especially the winter pole in the south, you have a too strong of a polar vortex because you don't have the proper wave forcing to slow it down. So there, it's a whole atmosphere problem. And more generally, these are some of the points why you need high resolution capability. I mean, resolving mesoscale gravity wave is definitely one of them. But if even for climate weather system, this this dark energy in the climate model, I heard this, listened to this talk by Bjorn Stevens from Max Planck last AGU, and he was talking about the importance of mesoscale shallow convection, which is very important according to their study for the cloud climate feedback. And that's not well captured. And he's arguing that you really need to go down to mesoscale to capture that, and of course deep convection. But somewhat all these blue items you have a little bit handle on because you have some parameterization to take care of certain aspect of that. And this ones you really need to resolve the wave directly because these are all direct perturbative effects by the waves. So if you don't resolve the waves, you don't get them. So these are some of the reasons why we need a high resolution capability.
So
And
that's
that's
actually a good
yes.
question. You separate the two modes where subgrid parameterization is good enough and where it breaks apart.
You mean this items?
Yeah. What's the major difference between, like, why can you not parameterize the red ones?
Oh, you are asking why you cannot parameterize the red ones?
Yeah, exactly.
Oh yeah. So this all this are, here what's important is a certain quantity associated with the mesoscales. For example, the gravity waves is that the momentum or energy flux that's carried by the wave. So if you have a smart way of guesstimate what that momentum is and how much it deposits in each layer, then you are more or less okay. So that's the parameterization scheme we have. Is we have some very crude way of saying how much waves are generated in the source region and how they propagate in the wind system and how much they would deposit at different, according to the background temperature, wind, and stability. So you have some way to do that. I mean, to prescribe those kind of momentum flux or energy flux and their deposition. But for this ones, you have to have the direct, the perturbation part, the temperature perturbation or wind perturbation, which determines either the chemistry process or the cloud, the polar mesosphere cloud, and the plasma variation. So there's no other way. You have to, directly resolve how big that perturbation is or how much that bubble is moving. There's no other way to alternative way to prescribe prescribe that. You have to resolve that. I'm
So
not sure if I'm making sense.
let me see if I got your previous thing right about the difference between the what's called the approximations. It sounded like you were differentiating between scalar and three-dimensional kinds of approximations, where in scalar, at the top, you don't care about directionality of where, like, wind is coming from or something. It's like deposit energy, whereas the more complex ones, directionality, 3D structure, internal really starts mattering. So whatever you approximate, you better represent it.
Actually, it's it could be it's not just a scalar thing. For example, it's like some of this, actually maybe it's easier to point to an animation I will show later.
Yeah,
but
please.
say maybe I'll do that. Yeah, let's look at this. Okay, so for example here, these are just wind. But this is wind at the surface, meridional wind at the surface, and the meridional wind at about 100 kilometers from the model. So, like this kind of perturbation, they clearly, the wave propagation, for example, they clearly have a direction. They are, there's a wave vector. They propagate to certain directions, and you do care about that, which way the wave is going. And on the other hand, you also care about the parameterized part. Say, if such a wave breaks, like here it's doing right now, if it breaks, some portion of its momentum will go into the mean flow, affect the large-scale circulation. So, for example, here, if this wave breaks, it may deposit a northward momentum to a northward forcing on the mean flow. So that kind of, so in both cases, both the mean flow part or the interaction or the energy deposition part and the perturbation part, this would be a subscale if you use a lower resolution model. Both would have a directionality to it. So
got it.
So yeah.
So directionality is a key differentiator between the easier and the harder cases.
Yeah, I think basically what I was saying is that maybe this is a good way of doing of saying this. This, to some extent, you can think of as some average effects over a certain, over say a wavelength. So the net effects averaged over one wavelength or certain wavelengths or certain scales coming from the wave system. So you don't really need to know the details of the wave. You can get by if you have a good guess of what the wave is doing to the momentum, to the energy. So that's a kind of a mean quantity. It's a bit like in the turbulence model, you think of what do they call Reynolds stress, right? So this is the kind of like a Reynolds stress. It's momentum flux. So you as long as you come up with a scheme to prescribe that, that's okay. But here, I mean, there's no alternative. You have to go to that scale and model that scale and see exactly what the fluid particles are doing.
Got it.
And it's not an average effect. You have to know the perturbation.
That makes a lot of sense. Thank you.
Sure, yeah. So that's what we're doing, trying to develop this new model, the CEMA model, and we're really targeted for the CEMA WACCM-X project. We're really targeting the high resolution. So we now adapt the new dynamical core, the species-dependent spectral element dicore, and we're solving things on the cube sphere grid, which the advantage is there's no polar singularities, unlike the old lat long grid, and which is really both increase the computing efficiency and also good for physics. You don't have to filter out the physics. And also for the thermosphere, you need a molecular viscosity and diffusion. Those are becoming important. And this is the cube sphere grid in the model. And then also, because we need to solve both in the atmosphere system and also the geospace system, which is organized by the geomagnetic field, we need to develop a regrading scheme to go between the two. And this is the resolution configuration we're talking about. The high resolution we go so far is at 25 kilometer horizontal, 1/10 of scale height in the vertical. And this is a control with an older, the usual resolution we have. And with that, we recently completed 1 year of we call nature run, and under solar moderate conditions, and there's no geomagnetic storm. So it's quiet, and we saved a bunch of fields, and limited by the the storage. We usually save 6 hourly output for some of the key quantities as the highest frequency, except some of the 2D fields that we can save every time step. But we do save restart files every 10 days, so we can do branch runs. Like recently, we have done the Hunga-Tonga impact simulation, storm time simulation with a coupled magnetosphere model, and eclipse simulations. We already saw this, so we can skip this. But let me explain first. This is from the whole atmosphere model, 25 kilometer, and you can see that there's in the lower atmosphere there's a tropical cyclone developing, and then the wave generated by that you can see much clearly higher up. Here the wave magnitude is really small, but because of the amplifying effect, when you get to the upper atmosphere, you see a lot of waves coming out from that. And actually, this is the magnitude of the wind. So you can see the wind magnitude is much larger up there. And also, the temporal scales are much faster. This is on the same time scale, frequency, and 3 days of simulation. So things are much faster, happening much faster with much smaller scales, as well as large scale. You can actually, in the background, you can see large tides going westward. And superposed on that are the small scale waves. And this is the kind of its manifestation in the plasma environment. This is ionosphere. So this is what's called the TEC, total electron content. So mainly from the integrated ionosphere plasma density, and it's filtered with a period of less than 2 hours. So it's a high pass filter, and you can see a lot of wave structure driven by the gravity wave. So gravity wave is really driving the plasma environment. This is the kind of thing we were trying to capture with a high resolution model, because this kind of perturbation, it's very hard to I mean, I don't know how you parameterize. Maybe you can have a large scale model and then come up with a smaller grid and try to guess what the oscillation is like within it. So maybe that's the only possible way. Maybe in the future, AI can do that, can fill the blanks in the future. But when we have that kind of a wave simulation, and we feed it to another model, the model developed by Jill Huber, it's called the plasmasphere model. That's a ionosphere plasmasphere. It's even higher. It's a real geospace model. We see some really interesting difference between the same model setup, SEMI-3 setup, with climatological forcing and with WACCM-X forcing with waves. And now you start to see the depletion of the plasma, the so-called plasma bubbles in the equatorial region. And he compared that with the gold observation, and you see the plasma density depletion qualitatively, at least, very similar to the gold measurement. And this really addressed the kind of issue we talked about earlier, the space environment aspect with ionosphere anomalies that can affect, telecommunication and navigation. And actually, if you go higher, this is several Earth radii. I can't remember the exact number, but this is with isosurface of electron density at 5,000 per cubic centimeter, and this is 1,000, so even higher. And again, this is a climatological model driving. This is a WACCM-X driving, and you can see this kind of what they call the plasma duct structures, which you do not see if you have climatological driving. So the resolution resolved waves was really producing. You can see that directly their effects, and such plasma duct has been observed in satellite and also radar, ground-based radar observations. So you can see the streak structure very similar to what has been simulated. And this is just a quick example showing the Tonga run I just mentioned. This is the lower panel is the surface pressure perturbation, and the upper panel is the TEC perturbation, the ionosphere perturbation. So you can see with that Tonga generating this LAM wave propagating globally, that has a big impact on the ionosphere. And I think in actual observations, the stations around the Earth, for the upper atmosphere monitoring stations, they saw it pass like 3 times. So it's a really big signal. And the models now with a high resolution, we're able to capture those kind of perturbations.
But and that was a volcano or something?
Yes, Tonga is a volcano eruption in 2022.
Gotcha.
Yeah. Yeah. And now we turn to the mean effects, the effects that we thought we have some handle on using parameterizations. So all those, what I talked earlier, were perturbative effects, and this is the mean effects. So here, we're looking at the color contours are the mean forcing in the zonal direction and meridional direction. And the line contour, the wind, actual zonal mean zonal wind. And you can see that the wave forcing, the color contours, are really responsible for, in the middle atmosphere, reversing the jet, either slow down or reverse the jet because of their forcing. And then the magnitude of the wave forcing is even larger in the thermosphere. This is the forcing in terms of meter per second per day. So it exceeds 100 meter per second per day in the thermosphere. And then with a similar magnitude here in the meridional direction that runs against the general circulation. You can see this is the northward, solid lines northward wind. So this is the summer to winter circulation in January, and summer is here. So the wave forcing is really running against the dominant prevailing wind. And what that does is that this creates a condition, the Coriolis force from the zonal wind would create a new wind balance that changes the mean circulation. So we're plotting out here the mean meridional component and the vertical component of the circulation in the northern hemisphere, in the northern hemisphere and the southern hemisphere. This is the, again, meridional and the vertical component. And the dotted line is compared with the low resolution model. So you can see that in the northern hemisphere, because of this Coriolis force, the new wind balance, everything is slower. The meridional and the vertical components are weakened by the gravity wave forcing. And it's opposite in the southern hemisphere. The equatorward forcing makes kind of accelerated the meridional and vertical circulation in the southern thermosphere. And what that does is it has a big impact on the thermosphere composition. So the net effect what we got is in both hemispheres, you now get a net upward circulation because your downward circulation is weakened and upward circulation is enhanced. So you get a net upward circulation. And what I'm plotting here are the profiles of atomic oxygen and molecular oxygen. They have the opposite gradient. And the atomic species become more abundant going up. So this kind of circulation change would decrease the atomic species and increase the molecular species. And as a result, if you look at the O2N2 ratio, the key quantity I mentioned earlier, we see that there's a big drop from the low res to high res, and which makes it much better agreement with the Gouvy observation now. It's still, we are not there yet, but it's a better agreement than before. So we're moving in the right direction. And this really addressed the issue I mentioned earlier, the how to better specify the density and composition of the space environment, which is really key for satellite tracking. So that's that. And then if we zoom out a little bit, look at the circulation we're looking at is only the thermosphere. So now we're looking at the vertical wind, mean wind circulation for the whole atmosphere, from the surface all the way to the upper thermosphere, from the high res and the low res. One key difference we see around 100 kilometer is this. In the low resolution case, we see a pretty much kind of almost uniform upward flow. This is upward. I mean, because of the large dynamical range, I use a non-uniform scale, but this greenish color is a weak upward flow. So what that does is that it will pretty much tend to prevent downward transport of species like nitric oxide generated usually in this region, in the polar night region. But it's and I was just plotting out schematically. So there's the summer to winter circulation driven by the gravity waves and upward, and then return flow at converging with the thermosphere branch of the circulation. So this is what we have known for many years from the low resolution parameterized gravity wave runs. But now with the high resolution, we get a very different picture. Now we have flow channels going both upward and downward. So you have a lot of flow channels and very localized downward mean circulation. And actually you can see the difference if you cut through, say, at 100 kilometers. This is the difference. So you have upward flow, but also very strong downward flow in comparison with the red, which is the mean circulation obtained from the low resolution model. So that would make a big difference in nitric oxide. And indeed, if we look at the nitric oxide in January from the high resolution and the low resolution, in the polar night region, we see a huge difference. And because now we have much more transport going from the lower thermosphere to the middle atmosphere. And this is just a profile at 80 degree north in the polar night region. And you can see this is a log scale, so very big difference. And this is another view of this difference of the nitric oxide in the polar enhancement of the nitric oxide in the polar region. But what that does is it can, I mentioned earlier, catalytically destroy ozone. So if you look at the ozone in the model, now compared with the low resolution model, you have a very strong decrease of ozone, both in the mesosphere peak and even stronger in the stratosphere, upper stratosphere peak. So this is really give us a tool that can now really address this kind of issues, the downward coupling issues that we cannot do very well before. So now, are we there yet? So this is the regular resolution, 200 or 100 kilometer we usually use for our everyday use, model runs, climate runs. And that can effectively resolve waves over 800 kilometers or so. But now we drop our resolution to 25. These are the kind of scales we can resolve. So usually they kind of divide the mesoscale, in atmosphere science at least, into two: meso alpha scale, which runs from 200 to 2000, and meso beta scale from 20 to 200. So now we can capture the meso alpha scales. So this is where we are now with high res. Is that good enough? One thing we can learn is, from observations. There's this very famous, well-known work by Nastrom Gauge. They measured atmosphere spectrum in the mesoscale range, and they found that despite the atmosphere complexities, the spectral structure is very simple. Looks very simple. You get a approximate minus 5/3 law in the horizontal spectrum for kinetic energy, and for the mesoscale. And increasingly now, with modern models, you can capture part of that spectrum in the global models, which is good. But of course, we're not there. We're not capturing the full spectrum in global models. Another thing is that the vertical wind has a very different spectrum. The vertical wind has a very flat spectrum, and that can also be captured by current models, again, partially. What that tells us is that anything related to vertical wind, any vertical flux, would have a very big contribution from smaller scales. And this is covers the momentum flux, energy flux, and species flux. So that tells us the vertical flux can be very important. And actually, we can do a spectral analysis. This is the relatively steep kinetic energy spectrum. And this is the momentum flux or other flux, energy flux, that would have a much flatter spectrum because of the flat vertical wind spectrum. And as a result, for the energy spectrum, the contribution from the smaller scales, the meso beta scales, would be 20%. So it's important, but not that important. But for mesoscale, meso beta scale contribution for the fluxes, that would be much more powerful, much more important. So this is a good example of the power of the powerless. The small scales are really having a big impact. So we're not there yet. Obviously, we stopped here, and we're missing still at least half of the forcing that we want. And actually, this is a quick estimate on the dependence of the contribution of various fluxes from smaller scale to large scale, and how they depend on the slope. This is the downslope. For a nominal, 5/3 law, you get barely 20% contribution. But as you for typical momentum flux, you get 50 or 60. And at some place, this is a plot of the spectrum from the model. And sometimes you get really shallow spectrum, and even almost flat. And then in those cases, the small scale contribution can be twice as large as large scale, or even larger. So this is a really important, why it's important to capture the smaller scale. This is another look. This is a contribution, relative contribution to energy density from large scales and smaller scales, and then the relative contribution to the momentum flux from large scales and smaller scales. And it's all percentage. So for energy density from large scales, is pretty dominating. Most places it's over 80%. There are some places at high latitude, the smaller scale plays a bigger role. But in general, it's red everywhere. It's very different for the momentum flux. So here, for example, if you look at the mid-high latitude in the northern winter hemisphere, it's over 90%. And in the middle atmosphere, below 100 kilometer. And even in the thermosphere, it can be over 50%, which is the white contour here. And so it's really plays a key role. And that's exactly why you cannot get by if you don't have any parameterization. You have to have some parameterization, try to capture this effects, no matter how bad they are in current situation. But this is a very important, and of course the question is, how do we quantify that small scale part? So this is the outlook part, and sorry, I'm a little bit late, but I'll try to finish in a few minutes. So this is the small. There are two ways I think going forward. One is that the parameterization will still be important because we cannot afford to run century-long climate runs or whole atmosphere climate runs with such high resolution. So we need to have a good small scale kind of subgrid scale parameterization scheme. And by good, we mean that we should avoid unnecessary or unphysical simplifications as done now in a lot of parameterizations. But one thing we can take advantage of is the scale invariance that exists in nature. And also we can start at least partially resolve. And because of the scale invariance, we can do the spectral extrapolation, trying to figure out what are the parts we're missing. So kind of in doing a statistical way. And that way, we don't have to make much simplification or assumptions because it's already done all right in the model, at least the resolved part. We only need to, deduce what's missing. So that's one thing we're working on is the scale aware. And the scheme we just mentioned is automatically scale aware because we're working in the spectral space. And the other thing, of course, is if we want to know better the physical processes by small scale waves, we go to higher resolution, even higher resolution than we currently have. And in the meteorological community, now they are running global models at convection permitting scale, which is less than 5 kilometer. And if we do that and then increase our vertical scale accordingly, I mean increase our vertical resolution accordingly, and also the time stepping accordingly, then we're going to the exascale computing. This is what we achieved using the Cheyenne computer, which is 5 petaflops. And so if we want to achieve this, we really need an exascale computing facility. And also it will require GPU enablement, of course. And that's what we are aiming for in the future with exascale computing, this kind of scale. And if we can get there, most of maybe all the gravity wave spectrum, the mesoscale, the full mesoscale spectrum could probably be resolved. And so that's hopefully, in the next 5 years, we can get there. So this is summary. So gravity wave from meteorological forcing, they're important for the space environment. I give you reasons for that. And then from the high resolution runs, we learn a lot about the physics. And going forward, I think two ways to better quantify the wave effects. One is take advantage of the scale invariance, devising better parameterization with less assumptions, unphysical assumptions. The other is, going exascale, trying to resolve the full mesoscale range. So that's it. These are some of the references if you're interested in more information. Thank you.
Yeah, fantastic. Thank you very much. This was excellent.
Yeah, thank you, Greg.